So let's go ahead and get started. It's 7 o'clock, so we've got an hour to get through basically a bunch of stuff that hopefully you won't forget beginning of the next break. So we've already went over recursive data structures earlier, right? We went over recursive data structures when we went over linked list again, right? So today we're going to go over the next big data structure because we've been taking basically everything we've done so far has been been some variation on the form of list, right? I even described stacks and queues as stupid lists, right? Because they could only do they could only do a small number of operations as compared to a list, and in fact you could use a list to stimulate them. Trees are completely different. They are a completely different data structure, but we'll be building them using the same methods we built a tree with, which is using nodes and connecting nodes together. The difference is that since we're going to be using recursion, the cases are a heck of a lot easier. It's also a lot less thinking you have to do in these because it's recursive. Believe it or not, recursion makes this much easier to do. And the terminology is actually pretty easy because we're going to leverage basically a bunch of vocabulary you already have that as relating to hierarchical trees, family trees and that kind of stuff, and actual trees. Now we're good at naming data structures, but we're bad at drawing. Okay, so we're going to be drawing our trees upside down. Don't ask why. It's just the way trees work. Our trees will be planted upside down with a root at the top and the leaves hanging at the bottoms of the trees. It's just the way it works. Don't fret about it. Maybe they're like zero gravity super sci-fi trees or something like that. So we're going to learn how to use trees. So we're going to go over We're going to go over trees, binary trees, and specifically we're going to go over binary search trees when we code them up. Now there isn't a binary search tree that's been created in Java. There isn't one like linked list. We're going to just write it ourselves. Trees are generally used to implement other things, but we're going to learn how to use recursion to process trees. We're going to learn about different ways to traverse a tree. Yeah, we're going to learn about the difference between binary trees, binary search trees, and then heaps. And then we're going to use trees to do some. We're going to use binary trees to do some, or specifically heaps, to do a basic form of compression. Well, not basic because when it comes to compression, nothing's really basic. But we're going to learn about how we can use it to compress. How to do like compression. Like how would you zip up a file? So this kind of problem. How do you make files smaller and preserve that data? So we're going to specifically learn how to implement these binary search trees using linked data structures and arrays. Heaps will learn about how to use arrays, and binary search trees will use doing linked data structures. Okay, so all the things we studied so far are linear, basically meaning we can only have a predecessor and a successor at most. Here, and we basically all the operations at worst case were O of n. Trees they're nonlinear data structures, meaning there isn't a clear path to iterate through everything in the data structure. It's a bit harder to iterate through a tree. They're hierarchical, meaning there's a top, there's somebody at the top and then there's people at the bottom. And tree nodes can have multiple successors, right? You get multiple people under you, but you only have one boss in these data structures. And that'll make sense in a bit because you'll see how those work. But in terms of big O notation, these when you properly create a binary search tree, it is kind of the jack of all trades. It is log n for everything. Log n to add something to a tree. Log n to remove something from a tree. Log n to find something in the tree. All those operations that we've been talking about. They should, when we properly do a binary search tree, specifically a self-balancing binary search tree, which is in Chapter 9, which is the most likely chapter to be cut, then all the operations are log n. Okay. So trees are really good at representing anything that's hierarchical, such as a class hierarchy, like we have in Java, like with object at the top, and then object subclasses, and the subclasses of those subclasses. A disk directory. Or subdirectories, right? The way data is stored on your disk is stored in a hierarchical manner. even though you just have a bunch of ones and zeros, that ones and zeros, from a conceptual standpoint, those are a bunch of, it's a hierarchy. Starting, if you're using a Mac, at root, and then you've got like the /user directory, you've got the /home directory, you've got the /bin directory, you've got all these directories which in themselves have directories. Okay, family trees can be represented by a tree. You know, they kind of make sense. They're recursive to data structures because they can be defined recursively, which itself is a recursive definition. Trees are recursive because they're recursive. But essentially, many methods can be but essentially the reason it is recursive because we can do all the hard work recursively, and that inside every tree, just like for a linked list, every list, when we learned how to look at it recursively, every node in the list we looked at him as though he was the head of his own linked list, right? Just like that, within a tree, every node in a tree is considered to be the root of its own tree. Okay? We're going to be focusing on binary trees, which means that these trees have two branches. You have two successors. And it's possible to do trinary trees or n-ary trees, as many kids as you want, but they can all be reduced down to a binary tree, and those are easier to deal with because there's only two things to remember there. And it is generally more efficient to do log n. So let's go ahead and get into the terminology right now because that's the easiest. That's basically, if you got to remember stuff from coming back, it's going to be this stuff, and this stuff will be easy for you to remember. So a tree is a collection of elements or nodes, right? So we'll be looking at it in terms of nodes, but each node holds elements just like a linked list. And each node is linked to its successors. So we've got dog, and we've got cat and wolf, and we've got canine, which doesn't necessarily look like it's sorted in a sensible manner, but I swear it is, okay? So the node at the top of the tree is called the root of the tree. So here, dog is the root of this very tiny tree, okay? So the node at the top is called the root. Remember, we computer scientists make terrible gardeners, so we're growing everything upside down, okay? Okay? The links from each node to its successors, the guys beneath him, are called branches. So the guys beneath you are called your successors. And you're linked to them by either what you can call links or branches. We're pretty agnostic for the terminology here, but it's a tree, so might as well use the term branches, right? Okay? You can call them successors, but honestly, that has way too many syllables. I prefer to call them children, right? So here, right, if you're on top, you've got successors, you can call them your children. And if they're your children, you're their parent. Parent. So the predecessor is called the parent. So that's the terminology we're going to use. Parent and children. So the parent node and the children node. Okay. Every node in the tree has exactly one parent, except for the root node, who's an orphan. Sad him. Very sad story there. But anyway, he has no parent. His parent is null in that case. Similarly, we can leverage this relationship to basically say other things like, oh, if you share the same parent, then you're siblings, right? These are sibling nodes. That makes sense, right? So what about dog and canine? What would you say their relationship is? Grandchildren and grandparent, right? We can do this. If we want to generalize this out, there's terms in English we can use for that, where canine is the ancestor of dog, and canine is the descendant of dog, and dog is the ancestor of canine, right? Ancestor basically generalizes the whole parent relationship of the tree. So I can have a lot of ancestors. Like my parent is my ancestor, my grandparent is my ancestor, my great-grandparent is my ancestor, and my great-great-grandparent is my ancestor. And honestly, at that point, I'd want to just probably say ancestor because that's less syllables than great-great-great-great-great-great-grandparent, right? So nodes at the bottom of the tree, right? We call this guy the root. Nodes at the bottom with no children of their own, they're called leaf nodes, right? Because like if you're, again, these are growing upside down, so you've got the root at the top of the tree, and if it's growing upside down, all the leaves are going to be up at the bottom of the tree, right? So if you have no children, you're a leaf node. We can all of them call external nodes because they're on the outside, and if you have children, you're an internal node because you're on the inside, but honestly, leaf is what we use there. Right, and again, they're getting into the parent. The generalization is the ancestor-descendant relationship. Dog is the parent of cat. Cat is the parent of canine. Canine is a descendant of cat. Dog is an ancestor of canine, right? All that stuff. All right. So the big thing about what this makes this recursive is that a tree is made up of subtrees, really. So every node, right, is the root of its own tree. Cat is the root of its own tree, made up of his left child of canine and his right child of nothing. Wolf is the root of his own tree, which is just made up of one node. That makes sense? Right? And dog is the root of his own tree, which has 3 other nodes in it. And canine is the root of his own tree, which has no nodes in it. Okay? We also have this term called level, which is basically how far are you from the root. It's how far you are plus 1, right? So if you're at the top, you're at level 1. If you're at the mid, then level 2, then level 3, then basically, that makes sense, right? Your distance from the root, right? It's a way, and you just can kind of look at that vertically and see what level you're at. Okay, can define that recursively. We'll leave that as a problem later on to solve that. The height of the tree is basically the longest path you can find from a node to the root to a leaf. So it's not 2 because while we can find a path from dog to wolf, the longest path is dog, cat, canine. Another thing about these links, generally we have in trees for solving like puzzles for the way this is going to work out, we generally have links to our children but not to our parent. Right? Our parent has links to us, but we don't have links to our parent. Okay. Let's see. So you may be wondering, okay, why in the world is this sorted like this? Well, it's because what we're going to be focusing on is something called binary search trees. So to first figure that out, we've been talking about trees in the general sense of the word right now. Now let's talk about binary trees. That just means that every node has 2 subtrees. Okay, so if you've got a bunch of nodes together in a group, and we call that group T, we can figure out if that group of nodes is a tree by saying if one of the 2 things is true. If that group of nodes is empty, then of course it's a tree. That's a base case, right? So the empty set is a tree, right? It also happens to be a list. It also happens to be a set, and it also happens to be basically anything else you want to call it. Okay. So otherwise, if it's not empty, its root node has 2 subtrees, TL and TR, such that TL and TR are both binary, can be arranged in binary trees, right? So this is a binary tree because dog has a tree to the left, cat and canine, and has a tree to the right, and both of these trees are binary trees, right? It's a recursive definition. I have 2 children, binary, and both my children happen to be trees. Make sense? I mean, there's not really a way for this not to work if you're working as a data structure. Yes.
The cat only has
one child, right? And his left child is a tree, and his right child is a set of empty nodes, which we say it's a tree if it's empty, right? Good catch there. Okay, so we'll see this. We'll see this later with expression trees, but basically we can store operands and operations in the tree here, but we can use trees for other things than what we're doing here. We'll get back to this when we start talking about we'll see this with postfix and prefix notation again, so we're going to jump back into that again at some point. But this is just showing that we can use trees to store things other than data, or rather than sorted data, which is what we're about to do. And Huffman trees are also another thing we're going to do, which use frequencies of occurrences of letters to figure out how to compress text. Rather, we're going to skip over that, and we're going to, again, jump back into them when we get into their actual section. Why go on a divergence when we can go on a roll and figure out why in the world is dog the parent of cat and wolf, right? Okay, well, it's because this is a binary search tree of strings. And the way a binary search tree works is that all the elements in the left subtree are before all the elements in the right subtree. In other words, all the elements that come before dog go into left. All the elements that go after dog go to the right. So alphabetically, wolf comes after dog. and cat and canine come after dog. But also, for it to be a binary search tree, all my left and right children also have to be binary search trees. So for this thing, it can't be we can't put canine here and then cat here because cat comes after canine. So it's easier if I show these things bigger on the board. So let's go ahead and switch over to the board because this is a small example. So let's go ahead and see what a binary search tree actually looks like. A binary search tree is a data structure. Basically, it's only going to work on sorted items. It's only going to work on comparables. So everything we do here is going to be comparable, meaning it can be put in an order. So here's an example of a binary search tree. Okay, 5, 3, 1, 4, 10. So first off, all binary search trees are binary trees by definition. They have a left tree and then they have a right tree. 10, 6, 12. Okay, so this is a binary search tree. Okay, now what it works out is that let's look at the root. All the elements that are less than the root are stored on the right side of the tree. All the elements that are greater than the root are stored on the left side of the tree. Got my rights and lefts confused there. Really got to work that out. So all the elements that are less than the root are stored on the left side of the tree. All the elements that are greater than the root are stored on the right side of the tree. And then that process is applied recursively. So here let's look at 3. All the elements that are less than 3 are stored to the left of 3. All the elements that are greater than 3 are stored to the right of 3. All the elements that are stored on this side of the tree that are less than 10 go to the left of 10. All the elements on this side of the tree that are greater than 10 go over here. So why is this such a cool? So why is this a definition of thing? Well, because it allows us to. Whoops. Oh, shucks. Oh, I'm sure it will wash right out. So why do I care? Why do I bother even doing this thing? Well, because this allows us to do binary search essentially on everything. So say I'm trying to figure out if 6 is in this tree, okay? In this binary search tree. What I can do is I start at the root, just like starting at the head of the tree. And I can ask, okay, is 6 in this tree? And 5 goes, well, I have no clue, but I'm 5, not 6. But if 6 is in this tree, it's going to be somewhere on my right? You can ask my right subtree. And because we're asking the right subtree, we're not going to even have to search the left subtree because that's all the stuff that's less than it. We know that all the stuff that's less than 5 goes to the left. 6 is greater than 5, so it's not going to be on the left side. So we can then ask 10, is 6 in your tree? And he's like, I have no idea. I'm 10. How should I know? Go and ask my left subtree because 6 is less than me. Okay, is 6 in this tree? And he goes, well, wouldn't you know it? I'm 6. And so I'll return true, he'll return true, he'll return true back to the user. So this allows us to do that binary search that we've been ranting and raving about, last week, which allows us to basically say, okay, if I look for something and I decide to go to the left, right, that cuts out half the items in the tree I have to look at. If I go to the right, that also cuts out half the items I have to look at in the tree. And then that process applies recursively. So I cut out half, and then I cut out another half, and then I cut out another half, and cut out another half. So that means that since I'm cutting out half each time, as I explained previously, that means that the search time for this is logarithmic, right? With a big honking asterisk, right? It's log n with a big honking asterisk. It's logarithmic if the tree is balanced, which is a word we'll have to get into. Because there's many ways to write a tree, and most of the trees that are actually implemented in practice are trees that are called self-balancing, which make sure that they stay balanced. And they can do that in log n time, so there's no penalty for doing it, except for the fact that the code for the simplest one I've seen is like 40 lines to do that. So yes.
So the tree sorts itself basically, right?
That as you add stuff to it, it keeps itself sorted. Yes.
What if there's double numbers? So
What if there's double numbers? That is a choice we'll have to make. What I do is that I treat I say that all the numbers that are less than or equal to go to the left. That's the choice I make. Some people say no duplicates and they throw it out. Okay. I say if we're gonna just so it's just the choice you have to make. The design choice I use for this class is that if say we add 5 to this tree, then 5 will be located over here, right? Because it's less than all the things that are in the tree that are less than or equal to this node will go on the left. Yes.
And you can only add it to the end, like at a leaf.
Yes. So you figured that part out. You can when we add stuff, we have to add it to an empty spot, and the only empty spots are going to be where leaves can go. So we'll get into how we do our addition, but it's actually pretty much all the algorithms work the same for. There's essentially 90% of the algorithms you have to use to solve a tree can be summed up into 2. Search or iterate. Those are basically the only 2 algorithms. All the questions, pretty much every question I'll ask you, especially the test questions for this unit, will be one of 2 variations. Either you search for something to put somewhere, so you're searching for a specific node, or you're iterating over all the nodes. In other words, here I decide to go left or right, okay, which means I'll do something in log n time. I decide to go left or right to look for something. Or say I want to print all the values in the tree, I'll like print myself, and then I'll print my left child, and then my right child, and then do that recursively, okay, which means he'll print himself, then print his left child, then print his right child, and he'll print himself and print his left child and print his right child, right, and that gets applied recursively, and that function just goes over everything. There's 2 algorithms, so essentially those are pretty much the 2 algorithms that you need to use for that. There's other algorithms, but they can be like, there's weird stuff like how do you start from here and go across? Well, those kind of data structures are weird. That was kind of weird. Okay, there's other kind of problems that can be solved, but you can use other data structures to help you, like hues, to basically. So for those remaining 10%, they can generally be solved by adding an additional data structure to help you out. Okay, so let's go ahead and look at some more examples. So let me add some more nodes. Like over here, 7. Is this still a binary search tree? Yeah. Okay, if I add a 0 over here, is this a binary search tree still? No. What violated? But 0 is less than 5, and it's on the left side of 5, so what's wrong? It's on the right side of 4. So would putting it on the left side of 4 fix things? No. Why doesn't it fix things? Because it's on the right side of 3. Right? These decisions have to be figuring out where to put something correctly is a top-down decision. You have to go from the top to the bottom to figure that out. Right? 0 is less than 5, it's less than 3, it's less than 1, so it goes to the left of 1. Okay? So now let's go ahead and start maybe with this. 5, 7, 6. 5, 7, 6, 10, 9, 8. Is this a binary search tree? Yeah, it is. It is. This one isn't very balanced. Because, and again, what does that, but you can visually see what it means when I say it's not balanced. Like everything is like, all the nodes are onto the right side of the root, right? And it's just all crooked looking and just aesthetically unpleasing, right? But we can't say, but we can't have like there's no really way to encode like aesthetics into the computer, right? I mean, maybe there are, but that seems like a bit of a hard thing. So there's actually a formula we'll be using to show that it's balanced, or mathematical definition to show that it's balanced or not. But this is an unbalanced tree. But let's look. All the stuff that's less than 5, which is nothing, is to the left. All the stuff greater than 5 is to the right. 7. So 6 is greater than 5 but less than 7. 10 is greater than 7, 9 is greater than all those things but less than 10, and 8 is greater than all those things but less than 9, less than 8. Sorry, less than 10 and less than 9. So this is a balanced tree as well. So now most trees, most trees when we see them in the wild and in production, they'll never be like this because they'll do stuff to keep themselves from being unbalanced. The trees, and that stuff is reserved for Chapter 9, self-balancing binary trees. Right now, the trees we're dealing with, they don't do that. They, on the worst case, might end up looking something like this. 1, 2, 3, 4, 5, right? They might look something like this, which is perfectly valid binary search tree, except it's more like a linked list because we're not taking advantage of any of the qualities here. So on average, so the big O for trees, what we're going to say is that on average, to do any kind of operation, it's going to be log n on average. But worst case scenario, it's O of n, because worst case scenario, we're dealing with a linked list, because our tree is super unbalanced. That's our worst case scenario. But on average is what we care about here, because in reality, we're going to have safeguard in reality, like real production reality. Okay, we're going to have safeguards in place to make sure that this never happens. And that's all stuff in Chapter 9, which unfortunately, if something's going to get cut, it's that chapter. So just because there's a lot more interesting stuff to go over. All right, so let's go ahead and go over more definitions now that we understand what a binary search tree is. Let's look at that formal definition for a binary search tree. So Control Shift. Okay, the formal definition of a binary search tree is that it's a binary search tree if either of the true is so 7 nodes T is a binary search tree if one the following is true. T is empty, right? If it's a null set, it's a tree, binary search tree. Otherwise, this bunch of nodes. Let's draw actually something else again. So 5, 10, 0, 3, 1, 1, 4. So something like this is a binary search tree. If we can separate it into if we can separate it into 3 parts: the root node, then the left subtree and the right subtree, and the left subtree and right subtree are both binary search trees, and the value in the root is greater than all the values in the left tree and smaller than all the values in the right tree. And that is a recursive process because, by definition, this has to be a recursive because left node and right nodes, say left tree and right tree, both have to be binary search trees. Okay, so as we've observed, it never has to be sorted because it's always going to be sorted. Okay, never has to be sorted because it's always going to be sorted for a binary search tree. Binary trees don't have to be sorted. They don't necessarily have to be sorted, but a binary search tree always has to be because you have to be able to search it. When we add in and remove elements, the binary search tree will stay in order. If we want to keep an array sorted, then that's going to take O of n time because each item is going to take O of n time to put into the proper place. And as we mentioned, if it's a balanced tree, which is a term I still have to define, it takes log n time to find something because we're going to optimally not have to look at half the remaining items. So here's the algorithm for searching. If the tree is empty, if the current subtree we're looking at is empty, then return null because we haven't bound it. Otherwise, if the root of the subtree we're looking at has the data we're looking for, return the data. Otherwise, if it's less than the root node, search the left subtree. Otherwise, if it's greater, the only option is that it's greater, so we search the right subtree. Question?
What's linking? Like, is it like a linked list where there's like a next
Yes.
or something?
Yes. So how are these things organized? Excellent question. We will use a node class just like we used for linked lists, and it's going to look like this. So I might as well write it now since you asked. It's going to look like a private static And the reason why I had these things as private static classes inside of other classes is because we wanted to make sure that they were, basically we want to make sure they were independent. Private static node, and technically the E here will need to be extends comparable. But that's the only thing wonky about it. Private static class node. Will have, and just like everything else, it's going to have an E. I'm going to call it data rather than item this time around. Okay? I'm going to call it data this time around. Just another way to make sure that which node I'm talking about. Then we're going to have a node E, and rather than calling it previous or next, I'm just going to call it left, and node E right, and I'm going to use this, and I would use the same constructor, which is public node E data or item. It's up to you. The name's just a name. This dot data equals data. So obviously the magic of what happens is that we can is in the tree class, because honestly I could call this prev and next, and so long as I set the pointers in the right direction, in the right manner, it's all about how do we it's not how these are named, but how these are set up, right? That's what matters. But we call them left and right because it's easier than calling them A and B or prev and next. It makes more sense. Now occasionally you might have a third pointer, node E parent, that will point to my parent, but for most cases you don't need that. You don't want to go back up the tree. You want to just always go down the tree and keep searching it. But that's what your node looks like. And we just keep it comparable just because because all the data in the data structure is going to be comparable. It's going to be sorted. Otherwise, it's not going to be a binary search tree. Okay. So there's three definitions of trees. There's three words that describe trees: full, perfect, and complete. So full and perfect are very easy for students to understand, and you'll probably remember what complete means. So you'll probably remember what full means even after you take this class. Perfect you might have to review, and complete you'll probably be like you'll completely forget that you ever learned it until you have to review for interviews again. So, but that being said, they're pretty easy definitions. And then we'll be able to talk about balanced, which means that basically, I don't know if we talk about balanced. Now we'll have to get into that another time because that's the fourth term we'll have to learn, balanced. But right now we'll deal with 3 because 3 is easy to remember. 4 starts becoming difficult. So a full binary tree is a binary tree where every single node has either 2 children or 0 children. So let's take a look at this guy. Doesn't matter what the values are in here. All that matters is that every node either has 2 kids, right? Or they have no kids. So all these have no kids. If 2 were to have a child, a single child, right? Then it would cease to be a full tree, because to be full, everybody has to have either 2 children or 1 child. Okay? So a perfect binary tree. So the only reason full exists is because it makes it easy to define a perfect tree. A perfect binary tree is a full binary tree with a height of n, with n to the 2 to the n minus 1 nodes. Okay? In other words, this is a one of height 3, so it has 7 nodes in it because there's 2 to the n minus 1 possible places we can put nodes. If it was height 4, it would be 15 nodes, right? Because we could add 8 children underneath here, right? And then if it was height 5, it would be 31 nodes because we could add an additional 16 nodes underneath here. Right? So it's 1, 2. So we'd have, so a perfect binary tree would have 1 on the first level, 2 on the second, 4 on the third, 8 on the fourth, right? And so on and so forth. Until you got to height n, which would also be completely full, right? So basically, not only does everybody have the maximum, either 0 or 2 children, but basically the bottom level is completely full, right? And so every level is basically even, right? Visually, it's easy to understand, but there's the mathematical definition for it. If you're at height n, you have 2 to the n minus 1 nodes. Okay, does that make sense to everybody? You can easily visualize what a perfect tree looks like. And I'm going to even draw one over here, because I'll need to do a lot of drawing to explain complete, because while it's not a hard definition, there's a lot of good. It requires a lot of drawing just to hammer it home. So here, right? So first off, this is a full tree, and it is also perfect, right? Because it's 1 node, it's height 1, 2 to the n minus 1. So it's got or 2 to the h minus 1. So let's see. This is also a perfect tree. This one is just full, right? It's not perfect, but as soon as we add 2 more nodes over here, it is a perfect tree. Okay. So now about complete. A complete tree is perfect except for the last level, where it's just filled in, so a complete binary tree is almost perfect, okay? But there's some extra nodes on the bottom level, and they're all on the left side. So the best way to show you is by counterexample. So here we have a perfect tree. It is also complete. Okay. Now, if I remove this node, it is no longer perfect, but it is complete because this part, the uppermost levels are perfect. Okay, but the bottommost level is not perfect, right? It's got a bunch of nodes over here. But they can't all do, but that's just not the only definition there. If I remove this over here, this node over there, so we've got this structure over here, this is no longer complete. All the nodes have to be shifted all the way over to the left in a complete tree. So this is a complete tree, this is a complete tree, this is a complete tree. This is not a complete tree because we have a gap between the nodes on the bottommost level. See how we have a gap here between the nodes, right? We have 2 missing spaces between the nodes that are on the bottommost level. This is not complete because there's a gap between the nodes on the bottommost level. This is also not complete because there's a gap between the nodes on the bottommost level. Still a gap between the nodes on the bottommost level, right? This is complete though because there is no gap on the bottommost level. Make sense? Yes.
Is there like a reason to even define that?
Is there a reason? That is an excellent question. The answer is that for binary search trees, not really, but for heaps, yes. When we get into heaps, basically all heaps must always be complete. And also or rather, there's not a reason to define this for the way we're going to do our trees, because we're going to do them as with using nodes. But if we were using them with arrays, then it being complete would be the way to kind of count what indices that would be. For instance, this node would be at index 0. This would be 1, 2, 3, 4, 5, and so on and so forth. And if it was complete, that would mean there's no gaps in the array. There's no null values stored in the array. Does that make sense? So really just, it's not going to be relevant right now, but once we get to heaps, which will be after spring break, we'll have to review this definition and come back to it. Let's see. So, but yeah, why do we bother defining it? Because it's important for heaps. So a general tree is not like a military tree. That's just, it's not a military hierarchy. It just has to deal with basically you can have each node can have any number of children, right? Like a family tree, or if you're looking at the hierarchical descendants of like some, the kings or something. Here, we're not going to discuss these because you can turn them all into binary trees anyway, believe it or not. Yeah, it doesn't look like you should be able to turn this into a binary tree. It just requires tilting the perspective. But here's a general tree, right? William the First, his children are Robert, William the Second, Adela, and Henry the First, whose children are William and Matilda, and Matilda's child was Henry the Second, who has hit those children, right? So on and so forth. So how in the world can we restructure this? Well, it just requires a change in perspective. We can we can always take a binary tree and represent it as general tree and represent it as a binary tree. And the way we did this for this one is that your left branch is the oldest child, right? Your oldest descendant, right? And your right branch is your next younger sibling, like literal sibling, right? This is a family tree. So here, right, focus on Richard the First, right? His older brother was Henry, and his youngest brother was Joffrey, and Joffrey's younger brother was John. Okay? John had the kid Henry, whose kid was Edward the First, whose kid was Edward the Second, whose kid was Edward the Third. Let's go back, focus on Henry the Second, and let's try to find him down here. There's Henry the Second, right? So his child, let's see, Henry the Second, right? His oldest child was Henry. His youngest child was and this Henry had siblings Richard the First, Joffrey, and John. Right? So all we did was just kind of tilt the tree, right, on its axis. But there's a way basically there's always a way basically to present a general tree, a binary tree as a general tree. These general trees as binary trees. Especially when basically you can only have one parent, right? If you have one parent, you can do that. If we have two parents, well, binary trees, you can only have one parent, so that suddenly becomes a bit of an issue, right? So let's see, how much time do we have left? We have 20 minutes. I really don't want to waste it. So let's go ahead and talk about what tree traversals. So Alt Q. Let's just make sure